to formally welcome the speaker and to chair the session. Ramo sir, please take over.
Thank you, Dr. Praveen. Good evening, all, and good morning to Professor Nunzi. I'm delighted to introduce Professor Jean-Michel Nunzi, who is currently the Professor, Canada Research Chair. Professor Nunzi graduated from Physique Chemie Engineering School, Paris in 1982 and joined École Polytechnique for PhD on nonlinear optics of surface plasmons. He was hired as a full-time researcher in organic photonics at the Atomic Energy Commission in 1984 and became head of the Organic Devices Lab in 1995. He joined the Department of Physics at the University of August as professor in 2000, built the Plastic Solar Cells Technology Research Team, and he then moved to Queen's University as Canada Research Chair in 2006. He studies self-organization, organic and nanophotonics, the processing and physics of nanomaterials, and devices for life, energy, and sustainability. The articles of Professor Nunzi has more than 10,000 citations and has an H-index of 53 as per Google Scholar. With this brief introduction, let me invite Professor Nunzi to deliver the talk. Professor Nunzi, over to you, sir.
Thank you very much, Professor. And I'm very happy, and actually it's a very great honor to be part of that seminar series organized by Kochi University. So now I will share my screen and give my presentation. So my presentation is on, oh.
It is in the background.
Yes, I don't know what happened. I lost the link, so I'm trying to return because I don't see anymore my. Okay. Oh, no, it's not shared. I don't know. I have plenty of windows which are turned on. I should probably stop sharing and clear up my windows. Yes. So sorry, there is a glitch. So sorry about that.
Cette conversation va être enregistrée. I think there is another window which has opened up.
No, I don't know what happened. Sorry for the Larsen. I was connected onto Windows and I didn't expect that. Okay. So I think that you can see my my presentation, and I go to the presentation mode. So my talk today will be on photodetectors, and I will describe the reason why we need new kind of photodetectors for several applications, and what is your contribution. My contribution is with several co-workers. I have co-workers at Queen's University, co-workers at in Kingston at Royal Military College, and also in biology at Queen's University. And I will present several results that we have done in collaboration with University of Kanazawa, with Russian Academy of Sciences in Moscow, and with the Chinese Academy of Sciences in Shanghai. And of course, I will present results which have been captured by students in my team, students who are spread in both departments, in physics and in chemistry. I give the name of the graduate students at Queen's University. We have presently 6 students working in the team, and a postdoc fellow, Pardis Rofui. And I remind you that Queen's is on the traditional territory of First Nations in Canada, so we acknowledge their kind taking care of our land. And the reason why we are interested in photodetectors was partly disclosed in a review paper that was published in 2021 on the reason why we need enhanced sensors. The reason is that most materials, most robotic devices like drones are becoming independent. They are self-driven, and they have some responses which are guided by light and vision. Of course, we could restrict the light to what we see, but that is not exactly the way it should be. For instance, if you look at nature with the mantis shrimp, which technically is not exactly, biologically is not exactly a shrimp, but this is how we call them. That shrimp has 16 type of UV to near infrared photosensors. We have only 3 in the human eye, but they have 16. So they can discriminate wavelengths which are only 25 nanometers apart. And in addition to this, they can detect polarized light, vertical, horizontal, but also circular, right circular and left circular. So these animals are very, very evolved, you can imagine, in respect to their vision. And the question is, how can we implement such vision systems to robots? So, of course, it starts with photodetectors, which can be tricked in different ways to detect different colors. And that's the principle of color cameras, technically. So, for instance, if you have a white light detector, like a solar cell, you can change it by having some materials, some semiconductors which are a little bit different. For instance, in the case A, in the figure that I'm representing, you can have a narrowband material which will let all the light going through and will detect only one narrowband light, like here it's pictured in green with a green arrow. But you understand that with such a device, you lose a lot of light technically because you don't capture the other light. So there are other designs, of course, because people want to capture all the light, in which you can use also filtering. Again, filtering loses a lot of light. With such device like the case A, you can put a second detector behind which will capture the red and the third detector which captures the blue. And if your band gaps are properly adjusted and the sequence of material is adjusted, you can make a kind of like a triple solar cell or triple detector which can detect the full spectrum. And if the bands are narrow enough, you can multiply the number of colors and maybe reach the same status as mantis shrimp, which is not exactly like a series of detectors in the animal, but there are different situations. So you can use filtering, which is commonly used in white light cameras to detect specific wavelengths. You can use internal filtering, which is actually the same case as case A, but in which you have materials which are sequentially deposited. So the first one absorbs the blue, transmits the green and the red. The second one absorbs the red, and you can have a third one which will behind absorb the red, and it will do the job. You can use also microcavity resonances, which will enhance one color with respect to the other ones, and then make a sensitivity to specific colors. So this can be implemented with perovskite materials, and I'm starting with perovskites. Perovskites is a material that was recently developed, not discovered a long time ago, because it comes from the perovskite, which is the name of the Russian scientist who developed the structure. And people who are doing photonic know the perovskites, are supposed to know the perovskite quite well, because they make these ferroelectric crystals, which are used for photorefractive materials like the lithium niobate. And several ferroelectric crystals have the perovskite structure, which is 3 compounds, A, B, X3. So that is a typical structure of perovskite. In the case of the photosensitive perovskites used for solar cells and for photodetectors, X is a halogen, B is a heavy metal, and A is an anion, which can be organic or metallic, so different kind of cations. It's a cation. A is a cation, which different type of cations can be used in those structures. We have been working on with my colleagues in Kanazawa on the back contact. These materials need to be sandwiched between layers to collect electrons and the holes. So a typical structure is a transparent piece of glass, which is coated with a conducting material. Here it is FTO, which is fluorine doped tin oxide. And we deposit on top an electron transport layer, so it is a metal oxide typically. The perovskite, which is a methylammonium lead iodide perovskite. And a whole transport layer. We work also on the whole transport layer. The most common one is a spiro compound, kind of expensive. And then there is an electrode, which in that situation is a gold electrode. That means it's an inverted structure where the electrons are the holes are connected by the top, and the electrons are collected by the bottom. So we've been working a lot on these metal oxide electrodes, and we have committed a review paper. The perovskites have been these hybrid halide perovskites have been developed for the photovoltaic applications quite more than 10 years ago, in 2009 in Japan, and very quickly the power efficiency has been ramping up to 25%, which is very close to the already the maximum efficiency of silicon solar cells, which is in the range of 27%, so a couple of percent below still. And the power of these perovskites is still ramping up. But it's not only, there is a lot of work to do on these guys. For instance, the bottom layer, we have been working on the bottom layer with colleagues in Kanazawa to optimize the deposition of the bottom layer, which often is a titanium dioxide layer for the conduction of collection and conduction of the electrons. So you can figure out with the diagram that the light is absorbed into the perovskite. This is a light absorber, which is situated above the whole conducting layer. And this is an energy diagram, and this is just the distance, which is a vertical distance through that device, which is pictured in the second picture, picture B. And you can figure out from the electrons, from the electron energy levels, so that is energy of the electron, that the light is absorbed into the perovskite. The electrons are traveling through the conduction band. The holes are traveling through the valence band of the perovskite. The perovskite is a material, I must say, which is an interesting material for solar cell because the exciton lifetime is very short. Actually, the exciton self-dissociates into an electron-hole pair owing to the very large dielectric constant of the material. The perovskite is a lead perovskite, so the binding energy of the exciton in these materials is small. So the electron-hole pair can dissociate spontaneously in these materials at room temperature, which means that we are dealing with free charges, positive and negative charges, which need to be collected to their respective electrodes, obviously, for the photovoltaic effect to take place. And owing to the proper contact, the contact which will be adapted, hopefully a Homi contact, which will block the hole and will conduct the electrons for extracting the electrons on the left, and the Homi contact for the hole, which will block the electron and conduct the holes on the right of the figure. So if the contacts are properly designed and are properly uniform, it's possible to grow larger crystals. So everybody is doing a lot of microscopy to explain how the crystals of the perovskite is growing, because larger crystals mean less defects and longer lifetime of the electron-hole pair into the material, which means a larger probability of collection of the electron-hole pair and a larger open circuit voltage for the material. So there is a lot of work, and we have been doing that work, which was published in several papers. And for instance, here is another work in which the trick was to grow larger crystals. So to grow larger crystals, there are different techniques. It looks a little bit complicated. That's a lot of experimental work to optimize these materials. And using a combination of ionic liquids, which allow to have a material which has different weighting properties for the different solvents that are involved into that material. And different growth techniques, we are able to grow larger crystals which will also less wetting water, so that could increase the stability. So you can understand that there is a lot of work which is done, but the main thing to understand is all these materials are processed by wet processing, which in the contrary with respect to compound semiconductors, allow to fabricate, in principle, cheap materials, cheap device, cheap photodetectors. And that is the reason why we are working on these materials. You could also think why perovskite versus polymers. The reason may be in the end the price of the technology, because the perovskite is made with compounds which are mostly inorganic compounds or small molecules, which all of them can be very cheap. Meanwhile, it's not yet the case for polymers, which are still complicated materials to fabricate, which are covered by patents as well. So the price may not be dropping down sufficiently quickly for the technology to get, to get robust enough, and for people to work strongly enough to get the best performance for one single material. Meanwhile, in the case of the perovskite, the variety of material is large, but a little bit reduced with respect to the polymers, and the access to the technology is more open, considering that the materials are easy to synthesize, so they are less protected by intellectual property technically, which makes the development faster, and the possibility to have technology, I think, a little bit more realistic, to have a technology of wet processed material. So this is the thing with the perovskite. The technique we were developing with this seeded growth, starting from an ionic liquid prepared nanoparticle, allowed us to fabricate stable materials. Stability is always an issue with solar cells and photodetectors. And on the left, you see a figure of stability of our compound. Our technology is the one pictured in the red curve. With respect to different technologies, which are also well approved, not using the seeded growth of nanoparticles, from nanoparticles. We get a better stability under illumination, and a better stability. Of course, it's a power conversion efficiency, but this is for storage over long periods in air without encapsulation, and under not very high, but under humid conditions of 30%. Humidity, moisture is a principal cause of degradation of these materials, because they are composed of cations and anions. This methylammonium are cations, or formamidinium, ammonium. The Fa also is a cation. Cesium also is a cation in that situation. And all of these are cations which can be degraded. I mean, not degraded, but swollen by water, which ends up degrading the perovskite material. So these materials have a band gap that can be tuned by changing the method, by changing also the cation here, but by changing also the halogen. So just by changing the halogen, you can have different colors, and all these different colors and the spectral response can be, once you know the absorption, can be predicted in the final design by some calculus. And this is an example where we compared some polymer solar cells with methylammonium lead iodide solar cells to check the effect of the thickness. And we can robustly, in a controlled way, really the modeling with the photo response of the devices. And when you can do that, also you can predict what will happen if you stack different layers of perovskites with different band gaps, like in the first device of a photodetector that I was showing. But that case was to evaluate how much high efficiency you can extract. High efficiency closer to the, I mean, efficiency can be above the Shockley-Kayser limit if you are using a stack of solar cells, above the Shockley-Kayser limit for a single junction. If you use multiple junctions, these are called tandem solar cells. They are a little bit tricky to engineer because the so-called tunneling layer, which is here, requires some attention. It depends really on the different materials that you stack on top of each other, understanding that these are wet processed. So there is need for a compatibility of the different solvents that we are using. So it's not so simple, but it is doable, and it allows to reach high efficiency. And again, by modeling, you can predict which efficiency and which thickness of the layers, which is very important. You need to use to design the material and the solar cells. As concerns the photodetectors, you can tune the perovskite composition. And like I was saying, it can tune the band gap, the range of absorption. For instance, in the diagram A, that was taken from a review in Nature Photonics, this one, from a paper in Nature Photonics. So you can tune the absorption range of the perovskite. So this is still methylammonium lead halogen, lead halogen perovskite, lead halide perovskite. And by tuning the composition, the ratio between iodine and bromine, you can use iodine, bromine, chlorine, like cation, like halogen cation, which will lead to different band gaps of your perovskite. And then by using some thickness, again, in that paper, they were using different layer active thickness. You can tune the band gap. This one is tuning the band gap. The composition is tuning the band gap more or less into the infrared, into the red region, and to cut down the part of the absorption that is in the blue region. They use the thickness of the material, which allows to reduce the range of absorption. Another design was by using different kind of counter ions. Actually, by using different composition, you can make different kind of cation. You can make a two-dimensional perovskite, or you can deposit the two-dimensional perovskite by single layers, by stacking single layers by different techniques. And it can also tune the band gap and the range of absorption. With two-dimensional perovskite, the range of absorption is more narrow, and this is a way into which it's possible to make photodetectors with multiple wavelengths of absorption. So all of this allows to make multicolor photodetectors which are sensitive to not only the intensity of the light, but also its wavelengths over a range which is larger than 3 colors. I mean, to go beyond this and to deposit materials which can be, most of them, wet processed. So now I will talk about the graphene photodetectors. So graphene is well known for its properties. There is a direct point, which leads to a very large conductivity, very large mobility at that point, mobility of the electrons. But the most interesting property that is used for graphene for photo detection is a property which makes it also a good sensor, because when you have electron withdrawing or electron accepting different kind of electron acceptors or electron donors on top of a layer of graphene, you can shift the Fermi level into the conduction band or into the valence band, which starts from makes your graphene start from a conductor, and you can make you can switch the conductivity of the graphene simply by putting something on top, something which has any kind of interaction with the graphene, and then in a transistor configuration like this one, in which you have a gate which biases the bottom layer is a conductor with an insulator with two contacts, source and drain, and by biasing the gain you can restore the conductivity of your graphene, which makes a detector. I'm showing that paper because that paper was recently published, and they designed the graphene sensor with some ligands which were able to trap to detect the SARS protein, the spike. They had spike antibodies, and they were able to detect the presence of the spike antibody, which makes, by way of consequence, a CoV-2, a SARS-CoV-2 COVID detector. So I'm showing this one because that was an interesting result. You can do similar things for photo detection. The graphene doesn't absorb a lot of light. So in order to make a photo detector with graphene, we need light absorbers. And in a configuration similar to this one, the light absorber will create, of course, some electron hole pairs or excitons, which will change the interaction with the graphene and will shift the Fermi level of the graphene. The Fermi level of the graphene, again, which is exactly located at the Dirac point, which is crossing between my two hands, where the energy is vertical. And horizontally is a K vector, but it's a little bit different than the representation of energy I was showing previously. And you can make a photodetector. So the photodetectors we are using in that situation are very simple. We have a layer of graphene, which is a CVD deposited graphene on top of silicon oxide, purchased from a company. There are two companies selling this, one in Spain and one in USA. Probably other companies are selling these wafers. So the wafers are 2-inch wafers. They are kind of big already. And we cut little squares, like 1 square centimeter, like these ones. Actually, that's graphene CVD, graphene monolayer deposited on the silicon oxide on top of silicon. And we can design by this way transistors. So you have the two electrodes, one electrode, the source, the drain, which form actually an interdigitized network to have more conductivity, because the conductivity of a single layer graphene is not so large. It's large per unit surface, but the current, the resistivity of a single layer is still kind of large. The resistance, actually, not the resistivity. The resistivity is small. And to have sufficient conduction, so a small resistance, we use a stripe, which total length is a few centimeters. And we can bias the gate and measure the source and drain current. And then we deposit on top some quantum dots, and the quantum dots provide the absorption. And here is an example. The quantum dots are lead sulfide, which absorb in the infrared. And when we send light, or when they are under white light illumination, the quantum dot absorbs the light and generate electron hole pair, which shift the Fermi level of the graphene and change the conductivity. And then using different ligands, we worked on the ligands. Samane was doing the work. Samane, with a collaboration with Sharif University, did the work in the team. We have a shift of the conductivity of the graphene, which is detected by the currents between the source and the drain. The absorbance of the quantum dot is in the near infrared. So these are infrared sensitive photodetectors. And by using different quantum dots, you can tune the absorbance into the infrared. That becomes a different kind of photodetectors, because the photodetectors made from the perovskite were sensitive into the near infrared, but not well below 800 nanometers. Meanwhile, these ones can go down to 1.4, 1.5 microns. So it goes more into the infrared. And like I was saying, we worked on the ligands. So we used the formamidinium lead iodide ligands to replace the oleic acid ligands, which are technically what is used when you purchase these lead sulfide, or when you fabricate lead sulfide by current techniques. So we made a ligand exchange, and here is just a comparison between the liquid ligand exchange versus a solid ligand exchange. So one is by immerging the quantum dots into a liquid, and the other one is just by making the substitution in situ on top of the transistor. So these two kind of ligand exchange were probed, and these are the characteristics of IV characteristics of some transistors, field effect transistors, under different illuminations or different gates. So this is under different kind of illumination, dark light for the different samples, and this is under different gate voltages, which shows that we have effectively a transistor. And the results of that study were published in a new journal of chemistry quite recently, technically. So these are this is what we can do with graphene-based photodetectors. There is another kind of photodetector that we are working on in my team, which is based on plasmonic resonance. I will first introduce very quickly, although I know that there has been other talks on plasmon resonance. I first introduce quickly the localized surface plasmon resonance at metal nanoparticles, which when you have which allows us to make some photodetectors, some hot-electron photodetectors. So first we have to understand that when you have a metal surface, the metal is reacting to the light by creating actually the light is a dipole oscillation. So actually when you have a metal which is a good conductor, I mean which is at an energy which is higher than the so-called plasmon energy, the dielectric constant becomes negative. That means that the metal is acting like a mirror. Acting like a mirror, when you have a dipole that is oscillating, there is a dipole of charges in the metal, which is exactly opposing to this one, and which reacts to the light. It can couple a light on top of the surface of your metal, but of course the light, if it is reflected, will not go into the metal, and actually there is no charges into a metal because and no dipoles, or so no light into a dipole, because the electrons of the metal create polarization, which is always opposed to the polarization of the light that is coming onto the metal. So this is a thing which there is only at the surface of the metals that you can have a variation of the charge density, which creates a dipole, which can make a propagation of light, a polariton actually, on top of your metal, on top of the metal. If it is a plane surface, there are coupling conditions which require, owing to the dispersion of the energy of the electromagnetic wave propagating onto the surface of the metal. For the conservation of the momentum of the light, we need a coupling technique, which people use like either a grating or a prism to couple an electromagnetic wave at the surface of a metal, which is not the case in a nanoparticle, because a nanoparticle is small enough to break the conservation of momentum owing to the size that is way smaller than the wavelength of the light. So in that case, we send light onto a metallic nanoparticle. The electrons in the metallic nanoparticle are directly excited by the light. There is a coupling, and that polariton is coupled and is called the localized surface plasmon at the metal nanoparticle. This can be resolved by resolving the equation of interaction, Maxwell equation at a metal nanoparticle, which is resolved by the Mie scattering theory in that case. And there is, what happens is that the electrons of the metallic nanoparticle are excited exactly by the light, following the light, like the dipole of the light is oscillating, and the electrons react to this, so they go exactly, of course, in the opposite way. When the polarization is positive, of the light is positive, you get a negative charging, and when the polarization of the charge is negative, like here, you get a positive charging of your electron cloud, which means that the electron cloud is moving around the nanoparticle. Owing also to the small size of the nanoparticle, this creates an enhancement of the light close to the nanoparticle, which can be calculated by different methods. But the thing is that we excite localized surface plasmons. Localized surface plasmons at metallic nanoparticle resonate when the dielectric constant of the metal is equal to minus twice the dielectric constant of the material that is around, of the dielectric that is around, which technically responds into the visible, close to the UV as well. We can use this nanoparticle enhancement for different purposes. I can continue a little bit on this one. The absorption of the light by a metallic nanoparticle will be proportional to its volume. Because the dielectric constant of a metal is imaginary. So there is a part which is just a reaction of the light, which is in phase with the light, but there is a part which is in a phase quadrature, which corresponds to an absorption. And when we cancel the dielectric part, the real part of the metallic nanoparticles in the denominator, actually it makes an enhancement of the absorption, and we are left with absorption. So that absorption varies like the volume of the nanoparticle. But there is a second effect, which is seen when we monitor the transmission of a sample of nanoparticles, which is a scattering. And the scattering increases like the square of the volume of the nanoparticles. So the bigger the nanoparticles, the larger the scattering is. So with large nanoparticles, we can have a large scattering. And this is what we are using in solar cells by putting the nanoparticles on top of the solar cell. So actually, we use the so-called inverted structures. That's an organic one, in which we have glass coated with indium tin oxide. We have an electron transport layer, which is a zinc oxide, which contains the nanoparticles for the scattering. And then we have a photovoltaic absorber, which is a polymer composition, which is a very classical polymer composition, nothing very original there. And we have a hole collecting layer, not very original also, and a silver on top anode, which will collect the plus charge. That inverted structure was designed to increase the stability of the solar cells, and I will not develop too much. These nanoparticles were developed by a solvent method, by a solvent reduction of silver ions, a very classical technique. And we do not incorporate the nanoparticles into the absorber, because if you incorporate the nanoparticles directly into the absorber without coating them with an insulator, like a silica shell or whatever will insulate them, they will short-circuit the electron hole pair generation, because an electron flying close to a nanoparticle will be spontaneously attracted by the nanoparticle owing to the polarization of the nanoparticle. Then the nanoparticle becoming negatively charged by that electron will strongly attract a positive charge, a hole. And in consequence, they will recombine onto the nanoparticle, which will make a weird photovoltaic response with a large open circuit voltage, but a very small current that is flying through. So it's not very interesting for the photovoltaic effect because it short circuits the electron hole pair generation. So in order to use wisely the nanoparticles, we incorporated them into the electron transport layer, because there, into the electron transport layer, they can just conduct because they are conductors, so it cannot do a lot of damage to the photovoltaic efficiency. But interestingly, they scatter the light. And we see scattering by this absorption spectrum figured here, in which we see that the absorption spectrum looks like reinforced under the presence of the nanoparticles, which is the blue curve here. So the control layer is just the composition poly 3-hexylhalophane PCBM, which is a fullerene, a derivative of a fullerene. And with the presence of the nanoparticles, we see an increase of the absorption, which is very much reflected by the external quantum efficiency of a solar cell, in which the blue curve with the nanoparticle is mostly uniformly increased vertically, not laterally, not a variation of absorption. So it shows that it is mostly a scattering effect more than a specific absorption due to the plasmonic resonance. And it increases the photovoltaic efficiency. But we can design other photodetectors with these things, because actually we can use, for instance, in that case, a layer of nanoparticles which were deposited on ITO. In that case, it's a plain gold film that was deposited under a vacuum, but with it's not exactly a plain gold film. It's deposited under a vacuum onto a hot substrate. The hot substrate is glass with ITO heated at about 150 Celsius. And during the deposition, the gold, which doesn't wet very well the ITO surface, agglomerates into some clusters, like you can see on the figure. It's a scanning electron microscopy image in which the bars, the horizontal bars, the green one is long of 100 nanometers. So you see we have little clusters which are in the range of 50 to 100 nanometers. These things are not regularly organized, which means that they can resonate like plasmon, have plasmon, their own plasmon resonances, and they can sustain coupled plasmon resonances. I was showing a nanoparticle in which, when you sunlight, you have the cloud of electron which oscillates under the light if the light is propagating horizontally. In that situation, with a polarization that is vertical, the cloud will oscillate in this way. If I couple two such particles, actually they will oscillate like a full dipole, depending on the wavelength of the light, which will do something like that. So actually, the nanoparticles will oscillate in opposition of phase, and will create, actually, well, I can show it like that, like a J coupling in molecules, if you want. It's like a J coupling. If the nanoparticles are organized properly, they can couple like J coupling for the people who know the photochemistry of J and H coupling of materials, and create an absorption which will be in the infrared. I must warn that it is not obvious that they will always couple in a J coupling situation, because they can couple also in a H coupling situation in which the two dipoles are oscillating in opposition of phase, which will cancel the dipole, create a quadrupole, but that will not create any absorption or any interaction with regular light that is incident on it. With this random structure, which has a quasi-fractal structure, we can have an absorption that spans the infrared. Interestingly, it was absorbing down to 1.5, 1.6 microns. So we studied them with a laser at 1.5 microns. And we could see that we had the hot electron emission from these, as pictured by the photoresponsivity of a capacitor. So the device is just a layer of ITO deposited on glass, which we purchase, a gold film, which looks brownish when you watch at it. It's called, technically in the literature, it's called black gold, but we have a very thin layer, so the absorption is very tiny. And if you want to see the absorption, actually the glass plate is a 2 centimeter by 2.5 centimeters. There is a stripe on gold, and the gold is just creating that shadow that you see on top of an image of lotus flowers for the decoration of the figure. And we fabricate an air capacitor with a spacer of 30 microns, typically 20, 30 microns. And with that spacer, which is a spacer used when people design dye-sensitized solar cells, we fabricate this capacitor, and that is the response of the capacitor. Of course, the light is shopped in front for the capacitor to respond. And this is the response of the capacitor demodulated at the frequency of the shopper, of course, in millivolts when we send the light. Okay, so we have a photodetector made with these materials. So what happens, if you want to understand how the photodetector, have a hint into how the photodetector is working, the light that is polarized in plane of the film will couple this localized surface plasmon resonance that between these nano, I would say, aggregates that you see on the figure on the microscopy figure, on the SEM microscopy figure here, and they will create these charges and will eject hot electron. I will come back to the ejection of hot electrons, which will be then changing the polarization along inside the capacitor and create the photovoltaic that we have in our detector. In order to check that the photovoltaic was created by hot electron and to vary the quantity of hot electrons that we could extract, we used the polarized layer of dipoles, a layer of dipoles from nonlinear optical molecules. This dispersed red, actually this azo dye, we knew it was nonlinear because it creates a second harmonic generation and that it was stable under light. So we have here a second harmonic generation into that material, which is not a polymer, it's a molecular glass, which is quite stable under illumination for second harmonic generation. So we could pull the material by using corona pulling with a wire and a heated substrate. And we have the layer of molecular glass on top of the gold layer. So we studied that phenomenon and then we monitored the hot electron emission from this. So don't think immediately about the horizontal layer. I will say the horizontal scale. The photosensitivity is in the vertical scale. Depending on the polarization, we have different sensitivities, and I will explain why. But first, the thing is the gold film, the net gold film, is the green line that you can see in that figure here. With the azo material, the azo glass on top, there is no change. That means that the hot electron emission is not affected, which is understandable because first, the electrons are not traveling through the capacitor, they are traveling from the gold to the ITO. So if you put something in the capacitor, it can change only the dielectric constant, but the layer being very thin, it doesn't change significantly the capacitance of our capacitor. So actually the photovoltage keeps being constant. The photovoltage, if you want to understand what exactly the photovoltage in a capacitor is, it's the quantity of charge per unit surface that was generated divided by the capacity. So the photovoltage is just Q divided by C, gives you a voltage, which is a voltage that we detect. Okay. When I say the density of charges multiplied by the area, so the photovoltage is directly the quantity of charges that were generated by the hot electron emission divided by the capacity of the material. So in that situation, if we don't change too much the capacity, we have the same photovoltage that was detected by putting a layer of azo glass on top. But if we polarize the azo glass in two directions, we can polarize it positively or negatively and orient the dipoles. If we orient the dipoles towards the layer of gold, we increase significantly the photovoltage, like is a red curve. If we orient the dipoles towards the opposite direction, we decrease the photovoltage. So actually, your photodetector is sensitive to the polarization of the material. So we have a layer of material. It's sensitive to this one. To picture what is happening exactly, the gold and the ITO do not have the same Fermi level. When we put them in contact, the Fermi level get equilibrated because there is no net current flowing through the device. So the two Fermi levels are become identical by an exchange of charges from the exchange of holes, technically an exchange of charge of electrons from the ITO to the gold, because the work function of the gold is larger than the work function of the ITO, larger by typically 0.3 eV with standard materials. So that creates a barrier, a tunnel barrier for the charges, for the hot electrons to be emitted from the gold, because it is in the gold that the hot electron is emitted, into the ITO. Why do we have hot electron emission? That is complicated and simple. When I was saying that the electron cloud is wiggling, actually it corresponds to the Fermi level, which if I show the energy vertical with my hand here and the position into the gold nanoparticles, the Fermi level is wiggling inside the nanoparticle of gold. And that wiggling of the Fermi level makes like the sea has waves, and the wave can cross the triangular barrier. So it can be modeled. Crossing and tunneling through the triangular barrier or jumping above the triangular barrier is a phenomenon that can be modeled by the Fowler-Nordheim modeling, which is an exact analytical model to describe the tunneling of electrons through a triangular barrier, technically, into a metal, or from a metal into a dielectric, or from a dielectric into a metal. So this is exactly the situation that we have. And by orienting the dipoles, what we do is just we change the energy of the vacuum into which the goal is. That reduces the tunneling barrier and increases the probability of the electron to go into the ITO and be detected by our photodetector. The polarization sensitivity is a little bit different. It is because when the polarization of the light is inside the plane of the film, it is absorbed. When it is perpendicular to the plane of the film, it is not absorbed. So that polarization sensitivity is exactly this one. So we had the detector that was at slanted incidence versus the propagation of the light, and we are turning the polarization of the light. When the light is in the P polarization, we have a maximum of we have a minimum of absorption of that light because there is a component which is perpendicular to the film. And when it is in the S configuration, if you want TE configuration, we have a maximum of polarization that is parallel to the plane of the gold nanoparticles. So we have a maximum of absorption, and this is a situation. The third situation is S or TE, and the situation is P or TM. And this is how the photodetector works. I think that my time is over. So what I will do is I will skip a little bit of part, like the fabrication method for the nano antennas, because by fabricating nano antennas, we can tune the frequency of resonance of plasmonic. For instance, here is an example. We fabricated, these are gold, these are copper. With the gold, we can have quite monodispersed nanoparticles. These are 200 nanometer long nanoparticles embedded into an aluminum oxide matrix membrane, exactly. And nanoparticles the antennas create an absorption which is in the range of 1.2 to 1.4 microns. That can be tuned more in the infrared by tuning the length. We have other tuning techniques which are to fabricate self-organized metallic nanotrees under light. And my time is over, so I will skip the part which is on biasability and photodetection, and I will thank you for your attention. And this is a zoom picture of the team in the fall 2020. Thank you very much. I will stop sharing maybe. Oh, I will continue sharing if I have some questions.
Yeah. Thank you, Professor, for the excellent talk. I would like to have one question. You were mentioning about the hot electrons. So what is the typical energy that your hot electrons have, which can be detected?
You see, if they are crossing the barrier, they can have an energy of, they can jump above 0.3 eV.
0.3 EV. Okay.
So the energy can be quite high. Actually, people are using hot electron emission. You know, hot electrons emitted from a cathode can travel into a vacuum and can make an electron gun. So they can have a very high energy technically.
Yeah, because in plasmas also we have observed the production of hot electrons in laser-produced plasma. So can these be detected with these devices?
Yes, sure.
Because there we observe something about keV range.
I said the 0.3 eV. It was in the case of photodetectors. They just need 0.3 eV to travel through the barrier. But if you send a laser beam, infrared laser, onto a surface of nanoparticles, you see hot electron emission. You see visible light. So that visible light is an emission from a hot electron luminescence. There are electrons that are ejected into the vacuum level, and which recombine into the gold, and they emit a range of wavelength that extends into the UV. So if you have visible light, that means that you have electrons that can go above 3 electron volts. So when you say if you send intense enough light, you can go into into higher frequency range. I don't know exactly that one, but you know, the work function of gold is 5.14 eV. So if you can ionize and you are still the electron is not ejected far away from the gold, you can create very high energy electrons. We are not working with more than visible light, so I cannot go into the. I suppose you could emit higher energy light with this hot electron fluorescence, hot electron emission, which means that the electron has been ejected with very high energy.
We have a question posted in the Q&A box.
The thing is, if I come back to these hot electrons, I don't want to overestimate the possibilities. If you go with the hot electron emission, the thing is, you may melt your gold nanoparticles. Will they reform the same structure? If they were processed by self-organization like we have been doing, they will form again the same structure. But they may melt because it hits at the top of the nanoparticles. So these are experiments we have not carried in my team, but I'm just giving some tips on what can happen.
I think we'll take another question. It is in the Q&A chat box. I'll just read it for you. What is the effect of temperature and band gap on power conversion efficiency in perovskite solar cell? And how to select suitable material for electron transport layer for perovskite solar cell?
Well, that's a very good question. So the optimum band gap is same as calculus that is done to calculate the Shockley-Kessler limit. That means the optimal band gap is in the range of 1.5 electron volt, which the perovskite reaches. The lead iodide, methylammonium lead iodide perovskite has a band gap at 800 nanometers, which matches the requirements for to reach the Shockley-Kessler limit. There are other parameters to reach the Shockley-Kessler limit, which is charge recombination and photon recycling, which requires still some work to get fully optimized. But they have already the optimum band gap for solar cells. If you want to make tandem solar cells, they don't go enough into the infrared to make tandem solar cells. That's why people are combining them with to capture the infrared. They combine them with silicon and other materials to go more into the infrared. That's the first thing. So second question was ideal electron transport material. Still presently, the best electron transport material was titanium dioxide. Recently, there is a report on using no electron transport layer, but just a single layer of oriented dipoles. And people proposed a series of silanes to attach on top of the FTO substrate, on top of the oxide actually. And these silanes have dipoles that allow to fabricate efficient electron transport layers. So what is the best? Although we have written a review paper on that in that journal called Materials last year, we wrote that review. The best electron transport layer is still under development, but there is a combination between, there is a trade-off between stability and efficiency. The most efficient may not be the most stable. Titanium dioxide is excellent, but you need to find the right structure, of, the right crystalline phase and homogeneity of your material. So it's still complicated because after that you need to grow the perovskite. So there is the electron transport material, but there is also the ability to grow large crystals on top. And if the wetting characteristics of your electron transport layer, which will become the bottom layer onto which you grow your perovskite crystal, if the wetting capability is not adapted to the solvents you are using for your perovskite, you don't grow large crystals. So the technology is a little bit complicated. There is a lot of try and fail. Understanding what wettability is, so you need to measure the contact angle of your surface to be sure that you will form, that your solvent will spread evenly on your layer. So it's a wet process. There are a lot of
There is another question. How could solution process the tunneling layer on perovskite without affecting the stability of the perovskite? Do we need any special solvents and the glove box?
Okay. So yes, you need the special solvents. You need special solvents for the deposition. Was that about the layer of perovskite itself or the layer of electron hole transport materials? I misunderstood the detail because the two require specific solvents and the two require different conditions. The perovskite itself doesn't need to be deposited into a glove box technically. The perovskite film itself doesn't need to be deposited into a glove box. But then the layer that goes above the perovskite, which is a hole transport material, in the end, you need no water into it. And that layer that goes on top, owing to its dopants, becomes water sensitive, which becomes an issue. But still, the layer that is on top, the whole transport layer, doesn't need to be processed in a glove box free of oxygen. It's moisture that is more damaging the perovskite. So actually, the perovskite itself doesn't need to be fully prepared into a glove box. It's more moisture that is an issue, water. So if you can have a dry environment, like in a country without water in the air, it would work. I know in the period of the monsoon, it will not be the best situation. So you will have in the year, for instance, I suppose in Kochi, you will have the same in Canada. We have a lot of humidity in the winter. So in the summer, it will be terrible to fabricate perovskite materials. They will not work. Meanwhile, in the winter, they will work. So that's why some controlled environment is needed. We want some consistency during the year.
Yeah, we have another question posted by Narayanuni.
Yes.
He has asked, instead of corona polling, can we use a matrix material with a spontaneous orientation polarization to align the dipoles?
Yes.
With a 30 micrometer thick spacer, can we extract the photocurrent?
That is the second question. 30 micrometer spacer. Hi, Jean-Michel.
Hi, Mi. How are you doing?
Fine,
nice
thank
to
you.
see you.
Yeah. So a lot of discussion going on about this spontaneous orientation polarization. That's why I thought
spontaneous polarization is ideal. Actually, that's a very good question because I have a student, Rana, who is working now in my team, and we are studying the layers that we put on top of the gold nanoparticles. So presently, just the idea of spontaneous orientation, to make it simple, we use self-assembled monolayers because we don't need a thick material. So when you are if you think about an oriented material, of course, if it is an amorphous material, starting from an amorphous material like the layer of azo material we are using, it's not a single layer that is organized. It is dipole into the host. Actually, the host is a glass that are oriented, and it's not just a surface effect that we are using into our sample, but we are probing presently some self-assembled monolayers because to shift the vacuum level, we just need a layer of dipoles. So we are probing some dipoles, and on gold we use different materials, but presently we use thiols. There are other materials that can mine on gold.
Okay. Yeah, my second question was about that spacer. You mentioned it is 30 micrometer thick.
So spacer is just the spacer that we purchased from that company in Switzerland.
Because mostly these polymers,
yes,
I expect them to be dielectric. So how do you extract current?
But it's just purchased and we cut it with very roughly with a cutter. On the temple, we put the cutter and it makes a little square, a rectangle.
Okay.
Hello, I see you.
Yeah, now they permitted. Thank you, Pramod.
So yes, the spacer is a commercial one because okay.
Yes,
you are going a little bit quickly, but of course, if we make a capacitor, we have been playing at filling up the capacitor with different liquids, different actually electrolytes.
Can I have one more question, Pramod?
Yeah, you can.
Yeah, in that nanoparticle, when plasmon based enhancement in the power conversion efficiency, I see that the absorption doesn't increase much, only very minute increment. But your quantum efficiency and power conversion efficiency both they have drastic enhancement.
Yes,
Why it is happening? I didn't understand that.
Yes, it's a very good question. But it's because our thickness of material is not huge, so the material still has some transparency. I can go back to the transparency.
Yeah, 18th, slide number 18. I noted it.
There's still some light crossing the device. So actually, what you measure when you measure the absorption, you measure what is transmitted. When you measure the absorption, you measure what is transmitted, and you see that your absorbance, I don't know if it's not big enough, I don't know exactly the number, but it's, you see at maximum it goes 0.8, and what matters is not the 0.8. Yes, it's 0.8, so that means there is 20% of transmission. What matters is how much transmission we are left with. And so actually, by the way, what you see here, it's a OD, which is already the logarithm of the transmittance. Yes, as the inverse of the logarithm of minus t. What matters for the photovoltaic efficiency is not what is transmitted, is what is captured into the material. By having scattering, we have light which is scattered, so it doesn't go transmitted, it goes spread all over the material, and for that light the absorbance is increased significantly, and this is only the part that is absorbed, so that's why you can explain the variation, the tiny variation can explain. That one is not a logarithm. The external quantum efficiency is not calculated in logarithm. It's just percentage of photo-electron. It's a quantum efficiency, so it's the number of photo-electrons that are generated divided by the number of photons that were incident, not absorbed. Okay.
Yeah. Okay. Understood. Thank you. Thank you very much.
Okay. So it's a little bit of that's a confusion between log and linear, technically, if you want to make it simple.
Praveen, do you have any questions? You are muted.
Yeah, actually, I wanted to ask, what was the maximum shift that you could achieve in the graphene Fermi level?
The maximum shift?
Yes.
Not a lot. It's you know, if we have tried to experiment with an infrared laser at 10 microns. The infrared laser is about yes, 100 milli-electron volts. So we had a sensitivity to the infrared laser at 10 microns. So I assume we can shift like typically 100 milli-electron volts. I don't have the exact number. The exact number I can show is given by in the physical transistor. I have another figure, and it's in the publication we have recently had accepted at New Journal Chemistry. If you browse through the supplementary material, we have a shift when we make the transconductance data. Uni knows very well when we report the current, source drain current versus the gate voltage, and we can go from a hole type of conductivity to an electron type of conductivity. And most important is how much you can shift this. Yes.
Maybe around 0.2 to 0.3 eV, I think.
Yeah, I was saying 0.1, but this is what you said. It's maximum.
Okay. All right. Thank you.
And the field effect transistor is a good way to measure that, because you go from the positive from the hole to the electron transport regime, and the minimum is shifted by both the nanoparticles and the light. The nanoparticles shift it, and then the light can shift it back and forth as well. So this is a way to detect how many EVs you have, and the range is like 0.1, 0.2, maybe 0.2.
Thank you.
Okay, I will take this opportunity to.
I didn't show this data. Of I can maybe in the next lecture I will show that.
Sure.
This is given the result you are asking for.
Thank you for that answer. I will take this opportunity to thank Professor Nunzi for giving an exciting talk in our webinar series and being part of our Silver Jubilee celebrations.
Again, I repeat, that's a very great honor to be part of your very prestigious seminar series. Thank you very much.
And I also thank all the participants who have spent their time in this late evening attending the talk and being part of the interaction. Thank you all, and thank you, Dr. Narayani, also for being one of the panelists.
And I encourage anybody to, if we want to have a face-to-face discussion, the Zoom is not too bad.
Okay. So, we will arrange it someday. Thank you. Thank you all for joining.
Thank you. I don't know how to turn off.